For today's discussion here in Mechanics of Deformable Bodies, we are going to tackle the third part of the fundamental concept of strain and deformation. So for this discussion, we are going to discuss some more mechanical properties of materials, compute axial deformation of a body. We are also going to draw shear, stress, strain diagram and identify the critical points in that diagram. And the last one, we are going to discuss the concept of Poisson's ratio and generalized Hooke's law. Okay, so we will start our discussion with axial deformation. So for axial deformation, let's say we have here a bar, okay, of length L. Okay, and let's say that this bar has a constant cross-sectional area all throughout its length. And let's say that this bar is loaded by an axial force P here. Okay, so we assume that the stress caused by P is below the proportional limit. Okay, so that means that we can apply Hooke's law. Okay, so the formula for Hooke's law is sigma is equal to E times epsilon. Okay, so again, class, we can only apply Hooke's law up to the point of the proportional limit in the stress-strain diagram. Okay, so because the bar deforms uniformly, the axial strain or the formula for axial strain is epsilon is equal to delta over L, wherein delta here, this is the deformation, right, or the elongation or contraction, no, of the material, okay, over L. So L here is the total length, okay, and the axial stress, we can compute that, no, by this formula. This is sigma is equal to P over A, where in P here, this is the internal normal force over the cross-sectional area, which upon substitution into Hooke's law, okay, so class, if we are going to substitute the formula for epsilon and sigma in the formula for Hooke's law, okay, so we can say that this sigma, no, this is equal to P over A. So we will substitute that here. Okay, the value of sigma is P over A, and then equals E times epsilon. And let's say the formula for epsilon is delta over L. So meaning to say, no, we can generate this equation, okay, from the Hooke's law, no, by substituting the value of this sigma and epsilon. So the equation here will become P over A is equal to E times delta over L. So class, if we are going to compute, no, for the elongation or deformation or contraction of a material, but in this case, no, the deformation here, since this is acted upon by an axial tensile force, no, therefore the bar will experience elongation. And if you are going to compute that elongation from this formula, so this will become PL over AE, no. So we just manipulated, no, this formula. So if you're going to solve for delta, so that will just be this L will be multiplied by P, and then this E will be multiplied by A, right, to solve for delta. So this will now become delta is equal to PL over AE. So in order for us to be able to use this formula to solve for elongation, P here, okay, it should be constant. Okay, meaning to say, let's say for this bar, okay, so the value of the internal normal force, it should be constant all throughout this length L. Okay, since this is the L, no, that we are going to use also in the formula. Okay, so that force P should be constant. Okay, or the internal normal force P, no, it should be constant all throughout the length, okay, of this bar. And also the cross sectional area here, okay, it should also be constant all throughout the length L. Okay, and if the material here is homogeneous, no, okay, so meaning to say the modulus of elasticity E is constant. Okay, so again, class, we can only use this formula if the cross-sectional area is constant, if the material is homogeneous, if the internal force P is constant along all throughout the length of this bar. Okay, okay. Okay, so for composite rods with various properties, cross-sectional area, and or internal axial force, the total elongation is the summation of all the elongation or deformation computed separately in each rod. Okay, so let's say we have here this composite rod. So this composite rod is composed of rod AB, BC, and CD. Okay, so let's say for rod CD, no, if we are going to compute its internal axial force, no, so it will be constant, no, along its length, no, from C to D. Okay, so also its cross-sectional area will be constant, no, and same with its material property or modulus of elasticity, no, it will be constant from C to D. So we are going to compute its elongation or deformation, no, using this formula, no, from the length here will be the length CD. Okay, so same with rad BC and rad AB. So we are going to solve them, no, separately. Okay, and then after that we are going to sum them up, no. So for the sign convention, no, for the summation, no, so we will take the tensile internal forces as positive. Okay, so tensile force internal forces, this will cause the elongation, no, in the bar. Okay, and negative for compressive internal force. Okay, so this will cause the material, no, or the rod to contract, no. So we are going to use this sign convention class, ha. Okay, again, positive for tensile internal force and negative for compressive internal force. Okay. Now, in the case of members with varying cross-section, no, wherein the uh, cross-section, no, uh, or we can no, generate an equation from the geometry of the bar, no, so we can use integration here, no. So for this type, no, of let's say of rod, no, so here, if you are going to solve its elongation, no, we are going to use still PL over AE, no, but we are going to incorporate integration here. So as you can see here, this is P dx over A of XE. So this is actually the same with this formula also. So P and then dx here actually is the length L, no. So we are just going to sum up this differential dx, no, differential x, no, from 0 to L. That's what integration means, right? This is actually summation. Okay, so we are going to sum that up, no, from 0 to L. And P here actually is constant, no, given that it will be constant all throughout the length, okay? And then A of x here, so this will be the generated equation, no, expressed in x, no, taken or derived from the geometry, okay, of the rod, no. So E here, no, is this is the modulus of elasticity or the material property. So this will be a constant here. Okay, so we are just going to integrate this from 0 to L, okay, to get its deformation. Okay. For sample problem number 1, the steel propeller shaft ABCD carries the axial loads shown in the figure. Determine the change in the length of the shaft caused by these loads. Use modulus of elasticity is equal to 29 times 10 raised to 6 psi for steel. Okay, so this is a steel propeller, no? So as we can see here, no, we have here this load, 2,000 pound. Also, we have here 6,000 pound load, and we also have here 4,000 pound load. So here we are going to determine, no, the change in length, no, of this shaft, no, upon application of these loads. Okay, so let's start solving this problem. Okay, so for this problem, we are going to solve the deformation, no? So here, to solve this, no, we have to solve the deformation for each rod. Let's say for rod AB, rod BC, and rod CD. So to do that, no, we are going to use our formula here, since this is a composite rod, no, wherein the area here, the areas of all the rods here are not no, the same. Okay, so for rod AB, this is 0.5 inches diameter, no, while from B to D, no, 0.75 inches. So we are going to solve uh, their deformation, okay, separately. Also for B to C and then C to D, they actually have different internal normal force. So they will also be no, separated. Okay, and their deformation will be computed separately. So we will start with solving the internal normal forces, no, for each segment of this rod. So let's say for AB, okay, we are going to cut this here at this, any section actually here. No, we can cut this, okay, to solve for its internal normal force, and we will name that as PAB. So we will just sum of forces horizontal here. So definitely, PAB will just be equal to 2,000 pound. Okay, now for the next segment here, that is segment BC. Okay, so for BC, now we are going to cut this section here. Okay, we are going to cut this here, and then you have to involve the entire left segment, no, if we are going to cut this, no, at this section. Okay, so this will be 2,000 pound, and then we will have an internal normal force PBC here, and also we are going to apply equilibrium equation here. So summation of forces horizontal is equal to 0. So definitely PBC will just be equal to 2,000 pound. And take note, class, that PAB, this is in tension. Okay, so for the sign convention in the summation, that will be positive. No, if we sum up, no, the elongation later on. And also for PBC, this will also be tensile, right? So this will be positive. Okay, lastly, for the segment CD, so we are going to solve its internal normal force. Okay, so we can just use the left side, no, left side of, or right side rather, right side or right segment if we cut this here. No, but we can also use this, no, this part. No, if we are going to cut CD here, okay, we can use either the right segment or the left segment. So that will just give you the same answer. So if we are going to use the right segment, so this will just be 4,000 pounds. So it's PCD, definitely it's also just 4,000, right? If we use equilibrium equation. So same here, if we use the left side, no, so 2,000 and then 6,000 here. So if we sum them up, it will just be 4,000. And that will be compression, right? No, and here this is in compression, so in our summation later on, this will be negative. Okay, so we are going to solve na, no, for the deformation by using this formula. So this is summation of PL over AE, or the deformation of each segment, no. Okay, so we are going to solve for the deformation of segment AB. And then we are going also to solve for the deformation of segment BC and segment CD. So here, this is already in negative, since we know that force CD, no, or the internal force, no, in CD, that will be compression, no, so this will be negative. And for AB and BC, that will be both positive, no, since they are both tensile forces. Okay, now, substituting the values here for AB. Okay, so this is for AB. Okay, so the internal normal force here, which is P, that is 2,000, no? 2,000 pound. And then its length, no? The length of AB, so this is actually 5 feet. No, but since we have to be consistent with our units here, no, we are going to convert feet to inches, no. So because, no, the given modulus of elasticity here is actually 29 times 10 raised to 6 psi, right? So psi, that will be pound per inches squared. So let's just convert feet, no, into inches. So 5 feet, so that will just be times 12, no, to make it inch. No, so that will be 12 times 5, or 5 times 12, so that will be 60 inches. Okay, over area. So for the area of segment AB, so the diameter here is 0.5. So the formula for the circular cross section, that will just be pi over 4 diameter squared. So that will be pi over 4, 0.5 inches squared. So this will be okay since the diameter is in inches, no? So okay, so we have to be consistent in our units, no? Okay, so and then for E, no, that is given 29 times 10 raised to 6 pound per inch squared. So that is for segment AB. Now for segment BC, okay, so the computed internal normal force here is 2,000 pound also. So that will be 2,000 pound times its length. So its length is 4 feet, no, converted to inches. So that will be 4 times 12. So that will be 48 inch over its area is pi over 4 and its diameter is 0.75. No, pi over 4, 0.75 squared will be the cross-sectional area. Now, its E is also the same. That is 29 times 10 raised to 6 pound per inch squared. Now, for segment CD, again, this is negative, ha? So this will be negative here. So that will be PL over AE. So the internal normal force for CD is 4,000. And then its length is 4 feet, so times 12, 48 inches, over its area. So the diameter is 0.75 inches. So the area will be pi over 4 times 0.75 inches squared times its E. That will be 29 times 10 raised to 6 pound per inches squared. So if you're going to compute this in our calculator, okay, computing this in our calculator, this will give us 0.013581 inches. Okay, and as you can see here, the answer is positive, right? So this indicates that the elongation, no, of this composite rod, no, this is actually elongation. No, so again, the value is 0.013581 inches. So this will now be the answer. For sample problem number 2, rigid beam AB rests on the two short posts shown in the figure. So we have here this rigid beam AB. So this is rigid, meaning to say it will not deform. Okay, so beam AB will not deform. So this rigid beam AB, this is supported by these two short posts. So this post AC and post BD. Okay, so AC is made of steel and has a diameter of 20 millimeter, and BD is made of aluminum and has a diameter of 40 millimeter. Determine the displacement of point F on AB if a vertical load of 90 kilonewton is applied over this joint. So take the modulus of elasticity of steel as 200 GPa, and for the modulus of elasticity of the aluminum, that is 70 GPa. Okay, so here class, no, we are asked to solve the displacement of point F. So point F is here. Okay, so class, here, if we are going to apply this 90 kilonewton load, no, in this rigid bar AB, so there will be a reaction here, okay, and also there will be a reaction here. So the reaction forces here and here, no, that will compress, no, bar AC and bar BD. So bar AC, or the post AC and post BD, no, since they will be compressed, no, so they will be subjected to deformation. Okay, and if this AC and BD will deform, or let's say they will be compressed, no, meaning to say this rigid bar AB, no, it will be displaced. No, it will not deform, but it will be displaced because of its because of this supports or post, no. Okay, so this point F, it will displace. Okay, so let's solve this problem. Okay, so for this problem, we are going to solve the displacement of point F, no, upon application of this 90 kilonewton force in rigid beam AB. So, this post AC and post BD, they will deform, no, since they will be compressed. Okay, so to solve for that internal compressive force, no, so we have to solve first for the reaction here at A and B. No, so drawing the free body diagram of rigid beam AB. Okay, so this will be the free body diagram of rigid AB. Okay, so this is the applied 90 kilonewton force. So to solve for reaction here and reaction here, we can use equilibrium equation. So you learned this in your statics of rigid bodies, how to solve for reactions, no, for parallel force system. Okay, so to solve for, let's say, for reaction here at B, we can take moment here at A. No, so taking moment here at A, so this will just be negative PBD. So PBD, that will be the reaction force here in point B, no? So that will be times 600. So the assumption here is positive for clockwise rotation. So this will be negative since the rotation here will be about point A, no, of force BD. That will be counterclockwise, right? So that will be negative plus for this 90 Newton force, actually this is positive rotation, no, about point A. Okay, so this will be positive here. So the moment of 90 kilonewton about point A, that will be 90 times 200 millimeter. So this will be equated to 0, and we can solve for PBD, or the normal force or the reaction force here at point B. Okay, now for the uh, reaction here at A, we can use summation of forces vertical since we already solved for the reaction here at B. No, so summing of forces vertical, that will just be P sub AC plus P sub BD minus 90 is equal to 0. So solving for P sub BD, no, since PAC rather, since we already have PBD here, we will just substitute that here. So our reaction here at A is 60 kilonewton, no, as illustrated here. So the reaction here is 60 kilonewton and the reaction here is 30 kilonewton. So we are going to apply Newton's law of motion here, no? So this reaction, if we transfer that to the free body diagram of member AC or this post AC, okay, so this 60 kilonewton force, okay, so this will be directed oppositely here, no? So if this is directed upward here, if we transfer that to the free body diagram of member AC, no, or post AC, so this will be oppositely directed, ha? So this will be downward here, meaning to say the another force at its another end, it should also be 60 kilonewton and it should be in equilibrium. So if this is directed this way, so this force, it should be directed this way, no? And this will cause the post, no, to be compressed, no? So it will be compressed. Okay, and also for 30 kilonewton reaction, no, so if you are going to transfer that here at the free body diagram of member BD, no, so this will also be directed oppositely. So there will also be a 30 kilonewton force here, no, at the other end, no, to keep the equilibrium here for post BD. Okay, so from here we are going to solve, no, the elongation or deformation, no, for this member AC and member BD. So here, this is not actually elongation since they will be compressed, right? So this will be contraction or compression, no? So for post AC, no, we are going to apply our formula for deformation. Okay, so that will be PL over AE. Okay, so PL over AE. So to solve that, no, we will just substitute the values here. So for PAC, okay, so that is 60 kilonewton. Okay, so again, we have to be consistent, class, how with the unit, no? So here, the given modulus of elasticity is 200 GPa, no? So we will convert that into MPa, no? So that will become 200,000 megapascal. Okay, and megapascal, that is equivalent to Newton per millimeter squared. Okay, so for our internal normal force, okay, so for internal normal force, ha, that is actually computed, ha, okay, so if you are going to cut section here, any section here at this member, no, the internal normal force will be 60 kilonewton all throughout, no, so this will be 60,000 newton, okay, and since this is compression, no, let's say this is negative here, no, just to indicate if it's compression or elongation, ha, so this is in compression, so this will be negative here, excuse me. Now for the length, no, so the length of AC is 300 millimeter. Okay, so that will be 300, no, millimeter. And then for the area, okay, so the diameter is given here, so we can solve for area. That is just pi over 4d squared. So the diameter is 20 millimeter. Okay, times its modulus of elasticity, which is 200,000 megapascal. So solving for the deformation for post AC, so that will be negative 0.28648 millimeter. So this deformation, this will also indicate, no, the displacement of point A. Okay, so since this column or post AC, no, so since this will be shortened, no, so it will no, it will go down, right? It will be lowered. So this point A, it will be displaced, and the deformation of this member AC will be the displacement of point A, right? So that's how it will be lowered, no, that so this will be point A, no, it will be lowered 0.28648 millimeter, no, so that is ano, no, it will go down, no, it will go down. Okay, now for post BD, okay, so we are going to solve its deformation. Okay, and again, its deformation, no, it will be equal to the displacement of point B. Okay, so this will be delta B is equal to PL over AE. Okay, so for the internal normal force for post BD, if you are going to solve that, no, if you're going to cut section at any point here, no, so the internal normal force will be 30 kilonewton. So this is in compression, so this will be negative here, and we will convert this into Newton, so this will become 30,000 Newton. Now for its length, so that is the same, 300 millimeter. For its area, the cross-sectional area or the diameter here is 40 millimeter, no, given in the problem. So that will be pi over 440 squared times its modulus of elasticity. So this is also given. The given is 70 GPa, so that is 70,000 megapascal. Okay, so solving this, so the deformation for post BD will be negative 0.10231 millimeter. So the negative sign here, it indicates that the deformation is contraction, okay, so or compression. No? So here, the deformation again of post BD, that will be equal to the displacement of point B. Okay, so point B, it will be displaced or it will go down 0.10231 millimeter. Okay, so from this computed displacements of point A and point B, no, we can analyze it, no, by drawing, no, this displacements. Okay. Okay, so we are going to draw here, no, how point A, point F, and point B, no, will be displaced, no. So, again, point B, it will be displaced or go down, right? It will go down, and then also for point A, it will also be displaced. It will also go down, right? So, drawing that displacement, no. So for point B, no, we computed this already. So the displacement is 0.10231 millimeter. Now, so it will go down 0.10231 millimeter. Okay, so from this point, no, it will go down at this point. Okay, also for point A, no, for point A, it will be displaced and go down 0.28648 millimeter. So from this point, no, it will go down 0.28648 millimeter. So this length This is 0.28648 millimeter from this point up to this point. Now, if point A and point B, if they were displaced, no, of course, point F will also be displaced since this is rigid bar, no. So this is rigid bar, no. So this will be displaced this way, right? This will be displaced this way. So point F, no, it will be displaced from this point to this point. Okay, so we are going to connect this, no, the new location of point A and the new location of point B. If we connect them, okay, so here, this point F, it will be displaced somewhere here at this point. Okay, so we are going to compute this displacement, no, from this generated geometry, no, from the displacement, no, that will occur, no, in this beam AB. Okay, so from here, we can see that we have a trapezoid here, right? So we have here this trapezoid. So this is 0.10231, no, this length or this height, no. So this is also if we project that, no, so this is also 0.10231 millimeter, no. So we will have a triangle here, right? So from this triangle, we are going to apply proportion, no, to solve for this displacement. Okay, so this side of this triangle, so this is just 0.28648 minus 0.10231, no. So this is 0. If we input that in our calculator, no, 0.28648 minus 0.10231. So that is actually 0.18417, no? So that will be the height of this triangle. Okay, and the base of this triangle, this is actually 600 plus, no, 200 plus 400, no? So that will be 600. Okay, so from this triangle, we are going to apply proportion, no? So from here, no, let's say for this side or this height, no, this height, this from this point to this point. So this is actually the deformation or the displacement rather, the displacement F of point F, no, minus 0.10231. Okay, so this will be that height, this height. Okay, from the triangle, this height, from this point to this point. Okay, so divided by its length here or base. So this is 400. So that is also equal, not to this this height. So this is 0.184. So we already computed that, no? So that is just the difference of 0.28648 and 0.10231. Okay. And then its length or base is 600 millimeters. So from here, we can solve for the displacement F. So solving for the displacement F, okay, so this will just be 0. If we, solve this, this will just be 0.10231 plus 0.18417 times 400 over 600. So the answer for this is 0.22509 millimeters. So point F, obviously, it will go down. Okay, so this will be the displacement of point F. Okay, so this will now be the answer. For sample problem number 3, the cross-section of the 10-meter long flat steel bar AB has a constant thickness of 20 millimeter, but its width varies as shown in the figure. Calculate the elongation of the bar due to the 100 kilonewton axial load. So use modulus of elasticity equal to 200 gigapascal for steel. So, class, we have here this flat steel bar. Okay, so this is 10-meter long. Okay, and uh, its thickness, no, is 20 millimeters. So we cannot see the thickness here, no, since this is in two-dimensional. But its thickness is 20 millimeter. Okay, so we are going to use that, no, for the computation of area here. Okay, so its width, no, it varies, no, as shown here. So here, the width is this, no, so this is 40 millimeter. And here, no, at the other end, the width is 120 millimeters. So meaning to say, it is varying, no? So it varies linearly, no, from here to here, from here to here. So this is linear, no, so it is varying linearly. Okay, so here we are going to solve the elongation. So since the applied load here is tensile force, no, so this will cause the bar to elongate. Okay, so we are going to solve this using integration. Okay, since we can generate an equation, no, for the cross-sectional area, okay, of this rod, okay, or this bar, no, using its geometry. Okay, so let's solve this problem. To solve this, we are going to use integration. So the formula for solving the elongation or deformation will be equal to the integral of p dx over a of xe from 0 to L, which is, this formula is just PL over AA also, no? Okay, so from here, no, we have to generate an equation for area expressed in x, no. So let's say we have here this area, no, we are going to say that this length, no, since the thickness is just constant naman, no, so let's say this length is or indicates the area, okay, and the distance for this will be x, no. Okay, so we are going to take this here at the ano, no, here at the middle, no, middle of this bar AB. Okay, so from here, no, we are going to generate an equation. So this area, okay, at the middle, no, we are going to say that this will be the area expressed in x, no, that we are going to solve, no. Okay, so from here, no, if we are going to project this width, this is 40 millimeter. If we are going to project this, okay, if you're going to project this, so there will be a triangle here, right? Also here at the bottom. So this triangle are symmetrical, no. So this triangle, no, we can use this, no, to generate, no, the equation of a expressed in x. Okay, so this area, again, this is x distance, no, from point A. Okay, so we can use this triangle, okay, to generate that equation that we need. Okay, so we can apply proportion here, no, applying proportion here. Okay, so this side of the triangle, no, this is actually 120 millimeter minus 40. No, if we subtract that 120 minus 40, so the difference will be this and this, right? But they are equal, right? This side, no, which is the height of the triangle here at the bottom, and this height of the triangle at the top, no, so they are both equal, right? So again, 120 minus 40 will be this side and this side, so divided by 2, so that will be this, let's say this side. Okay, so that will be the ano, the side of the or the height, no, the height of this ano, of this bigger triangle. Okay, so that will be the height AB. So AB, that is the area here at point B, no, so that is this area minus the area here. Okay, so that will be divided by 2 to solve for this. Okay, okay, over its total length, no, or the base of the triangle, which is L. So we will substitute this later on, no, this length, which is 10 meter, no, but here let's just say that this is L. Okay, so by proportion, this is equal to this height, no, of this smaller triangle here, right? So this side or this height, no, we can solve this, no, this is A, no, so this whole width, this is A, no, let's say this is A. Okay, so A minus 40, which is this, so if we project that here, that will be this width, no, so divided by 2, no, we can solve this, no, this height. So that's what we need. A, again, A minus AA divided by 2 to solve for this, this height, okay, of the smaller triangle over the base of the smaller triangle, which is x. Okay, so from here, we are going to solve for this A, no, which is the A or the area expressed in x, no. So we are going to solve this A. Okay, solving that, no, we can bring down this 2, no, this both these two, no. So this will become A minus A sub A over 2x is equal to A sub B minus A sub A over 2L. Okay, so here we can um, uh, cross multiply this, no, so that it will become AB minus AA times 2x over 2L. So 2 will be cancelled, and then solving for A, so this will just become, this will be transposed, no, to the other side, so this will become positive. So this will become A sub A plus A sub B minus A sub A times x over L. Okay, so from here, this will now become the equation, no, of this area expressed in x. So this is what we need for this A of x here, okay, in the formula, no. So we can solve for the value of A sub A, no. So that is the area here at point A, no, or the cross-sectional area. So this is 40 millimeter times its width, or thickness rather. So the thickness given in the problem is 20 millimeter. So that will be 40 times 20. So that will be 800 millimeter. So we can also solve for A sub B. So that is the area here at point B, no? At this section. So this is 120 millimeter times the thickness, which is 20. So this will be 2,400 millimeter squared. Okay, so now we can substitute these values here, and also for length, no, so that is 10 meter, no, so we will use millimeter here, so converting that will become 10,000 millimeter. Okay, so substituting these values here, so this will become AA is 800 plus AB is 2,400 minus AA, which is 800, times x over L, which is 10,000. So this is 10,000. This is typo error. Okay, so this is 10,000. Okay, so if you're going to solve this, 2,400 minus 800 over 10,000, no, you can input that in your calculator. 2,400 minus 800 over 10,000. So that is 0.16. Again, this is 10,000 plus, this is typo error, ha? Okay, so this will now be the equation for A of x. Now, substituting that here, no, we can now substitute that. So this will be integration of our P is 10,000 Newton, 100,000 Newton, since this is 100 kilonewton. And then dx over A of x is 800 plus 0.16x, okay, times our E. So our E here, the given is 200 gigapascal, so that will be 200,000 megapascal, which is, that is Newton per millimeter squared, right? Okay, so from here, our limit will be from 0 to 10 meters. So that will be from 0 to 10,000 millimeter. Okay, so that will be our limit since we are going to sum up, no, all the elongation from point A to point B. Okay, so performing this integration, no, so we can divide 100,000 by 200,000, no, so since they are constant, so we can just take them out, no, from here, no, since they are constant, so we can bring them outside the integral sign. So again, that is 100,000 divided by 200,000. So that is actually 0.5, right? So that will be 0.5 integral of dx. So what will remain here will be dx over 800 plus 0.16x. So here, from what you learn in integral calculus, we can integrate this. So integrating this, no, we can use ln here, no. So this will become, okay, so this will become ln, okay, of 800 plus 0.16x, and we will have here this neutralizing factor of 0.16 here, no? So this will become 0.5 times 1 over 0.16 ln of 800 plus 0.16x. Okay, so we will evaluate this from 0 to 10,000. Okay, so substituting the upper and lower limit, no, that's how we solve definite integral. So this will become 0.5 times 1 over 0.16 ln of 800 plus 0.16, substituting the upper limit, which is 10,000, minus, so rewrite this, no, and then substitute 0 here, so minus 0.5, okay, 0. Okay, okay. Saan yung camera? Okay, so again, substituting the lower limit here at x, so this will be 0.5 times 1 over 0.16, ln of 800 plus 0.16 times 0. Okay, so solving this, no, you can input this in your calculator. So the answer for this is 3.43316 millimeter. So this is the elongation, okay, that we are trying to solve here. So actually here, class, you can input, no, from here. This equation, you can input this in your calculator, no, if you want to solve this faster, no. But you can also use this this solution, no. But you can just input this also in your calculator. Okay, so if you input that in your calculator, okay, so this will still be the answer. Again, the elongation here is 3.43316 millimeter. Okay, so you can now box that. So this is for bonus points. So in the composite material shown, compute the deformation each in rad AB, rad BC, and rad CD, and also compute the total deformation. Use modulus of elasticity equal to 100 gigapascal for all rads. So again, solve for the deformation in rad AB, rad BC, rad CD, and the total deformation. So what you're going to do is comment in the comment section your name, your section, and the item that you are answering. So the first students to comment the correct answer, no, for each item, no, will receive the bonus point. So maximum of 2 points, no, for every student. Okay. So we are going to discuss here another concept. So we are going to discuss the concept of Poisson's ratio. Okay, so when a deformable body is subjected to an axial tensile force, not only does it elongate, but it also contracts laterally. Okay, so the example for this, let's say we have a rubber band. No, so if you are going to stretch the rubber band will elongate, no, but at the same time, no, you will notice that its thickness and width, no, will decrease. No, if its length is increasing, no, the width or the thickness of that rubber band is decreasing. Okay, so likewise, if we are going to apply a compressive force on a body, no, so it will cause the body to contract in the direction of the force, and yet its sides expand laterally, no. So if you are going to compress naman, no, a material, no, so since it is compressed, it will be shortened, it will contract, no, but its length will be shortened, but its cross-sectional area, it will expand, right? So here, no, let's say we have this bar, no, so let's consider this bar having an original radius r. Okay, so the cross-sectional area of this bar is circular, so its radius is radius r. Okay, and we have here this length. Okay, so this solid bar, no, so this is the original shape. Okay, this is the original shape. No, so upon application of this force P, so this is a tensile force P, so this will cause this original bar, no, so this will be elongated, no. So this broken line, so this will be the deformed bar, no, or its final shape. Okay, so here this force elongates the bar by an amount of delta. Okay, so since it will be stretched, no, so there will be a deformation delta, which will be there will be half of that deformation will be at this end, and on the other hand will be half of that delta, no? So here, if the bar is or elongates, no, if the bar elongates here, no, so the circular cross-sectional area, it will be decreased, no? So here, this decrease, no, that is delta prime, no? Okay, so we will uh, use this, no, as the change, no, in the radius, okay, of the cross-sectional area. Okay, so from here, now we can solve for the strain. Okay, so for the strain in the longitudinal axis, no, so the strain here will just be the delta, no, so that is the elongation over the original length. Okay, so that's how we solve for the strain, no, with respect to the longitudinal axis. Now, for the lateral axis, okay, of this bar, no, so the lateral part of this bar will be the cross-sectional area, no? So here, the change in the cross-sectional area, so again, the strain in the lateral um, section, no, of this bar will be the cross-sectional area. So that is the strain in the cross-sectional area. So the strain will be equal to the change in the radius. No, so the change in the radius is described here as delta prime. Okay, so that is the change in radius. That's the original radius minus the deformed radius over the original radius. So that's how we solve for the strain, no, in the longitudinal and lateral axis or direction, no, of this bar. Okay. Okay, so we are going to talk about here the relationship of the strain in the longitudinal direction, okay, and the strain in the lateral direction. Okay, so in the early 1800s, the French scientist S.D. Poisson realized that within the elastic range, the ratio of these strains is a constant. No? So since the deformations delta and delta prime are proportional. So this constant is referred to as Poisson's ratio. So Poisson's ratio, this is denoted as small letter v, no, but this is actually a Greek letter and it is read as nu. Okay, and it has a numerical value that is unique for a particular material that is both homogeneous and isotropic. So homogeneous materials, these are materials that exhibits same elastic properties at any point in a given direction. While isotropic materials, these are materials that exhibit some elastic properties or same elastic properties in any direction at a given point. But to simply put, no, on a larger scale, no, so homogeneous and isotropic means that a material has a uniform composition. Okay, so stated mathematically, Poisson's ratio is equal to negative strain in the lateral direction over the strain in the longitudinal direction. Okay, so class, the negative sign here, no, it indicates, no, that one of these values, no, will be negative. Okay, because here, if the longitudinal direction or the strain in the longitudinal direction is elongation, no, so that will be positive, no, and if the longitudinal or if the strain in the longitudinal direction is elongation, so automatically the strain in the lateral direction will be contraction. It will decrease, no? So we indicate negative sign, right, for a decrease in length or ano, no, or cross sectional area, right, for a strain that is in contraction. Okay, so that is negative. Okay, so that indicates that here now, no, and likewise if let's say the longitudinal direction is shortened, so what will happen to the lateral direction? It will expand. No, so the negative there will be the strain in the longitudinal since it will be shortened. No, so either way, no, it will be negative. No, okay. So here, notice that these strains are caused only by the axial or longitudinal force P. No force or stress acts in a lateral direction in order to strain the material in this direction. Okay. Also, Poisson's ratio, this is a dimensionless quantity since this is strain over strain. No? And strain actually is dimensionless also. No? So, for most porous solids or non-porous solids, it has a value that is generally between 1/4 and 1/3. For an ideal material having no lateral deformation, when it is stretched or compressed, Poisson's ratio will be 0. Furthermore, the maximum possible value for Poisson's ratio is 0.5. So take note of that, ha. That is the maximum possible value for Poisson's ratio. No? And here, class, ha, if you are computing Poisson's ratio, no, let's say in a formula, no, so what the sign that we are going to use is absolute value. Here, this just indicates the concept that if the length no elongates, so the lateral direction or the cross-sectional area, it will decrease, no? So it will be negative here talaga, no? But we are just in our computation, we are just going to use its absolute value, okay, which will be positive. Okay. Okay, so in our previous discussions, we already talked about the normal stress strain diagram, no? So here, we are going to discuss the shear stress strain diagram. Okay, so if in the deformation due to normal stresses, we describe the deformation no by computing the normal strain. Here in the deformation due to shear stresses, no, we compute no the shear strain. Okay, if in normal strain, no, that is the elongation, okay, or the contraction of a material. Here in shear strain, this is the distortion, no, or the change in angle, okay, of the points in the material. Okay, so again, to review, no, the lengths of the sides of the element do not change, but the element undergoes a distortion from a rectangle to a parallelogram. So that's what happens, no, in a shear strain. Okay, so the shear strain, no, so this is denoted as gamma, no, and this is the angle, no, or it measures the amount of distortion, and this is expressed in radians. Okay, so as you can see here, no, so let's say this is originally a rectangle, but upon application of this shear stresses, no, so this rectangle, it will be distorted into a parallelogram, and this change in angle, so the change in angle here will be this and this, no, so they are gamma, no, so since they are distorted here and here, no, so that this will be gamma over 2 here and gamma over 2 here. Okay, so the behavior of a material subjected to a pure shear, no, it can be studied in a laboratory, no, and the test that will be done, the data from that, no, it can be used to plot the shear stress strain diagram, just like how we plot, no, the normal stress strain diagram. Okay. Okay, so the data obtained from the laboratory experiment, no, for a material subjected to a pure shear, it can be used to determine the shear stress and shear strain. Okay, and a shear stress strain diagram can be plotted. So just like in the normal stress strain diagram, okay, for the vertical axis, it will be for the stress. No, so this will be for the values of stress. So in this case, the stress here is a shear stress, and that is denoted as tau, right? And for the horizontal axis, no, so this will be for the strain. So in this case, the strain here is a shear strain, and that is denoted as gamma. Okay, so this is an example of a shear stress strain diagram, okay, for a ductile material. So like the tension test, this material, when subjected to shear, will exhibit linear elastic behavior. Okay, so it will have here a linear elastic behavior. So this will be the linear elastic behavior of this diagram, and it will have a defined proportional limit. So at this point, no, this will be a straight line from this point up to this point. So this will be the proportional limit, no? And here in this proportional limit, the stress here is tau sub PL, no? And then also, strain hardening will occur until an ultimate shear stress. So in this case, no, it will reach this maximum point. So this maximum point, this will be the ultimate shear stress or ultimate shear strength, no? And that is denoted as tau sub U. Okay, and finally, the material will begin to lose its shear strength, okay, until it reaches a point where it fractures. So this will be the point where the material subjected to pure shear, no, will fracture. So this will the stress here, no, or the shear stress here will be tau sub F. Okay, so for most engineering materials like the one just described, the elastic behavior is linear. And so Hooke's law for shear can be written as tau, okay, that will be equal to capital letter G times gamma. So again, this is Hooke's law, no, and this can only be applied, no, for the values of stress and strain until this point, which is the proportional limit, since only until this point or up to this point will this curve be a straight line. Okay, so we apply Hooke's law here, and take note here, class, that this G, this is another material property. So this is actually the shear modulus of elasticity. Okay, or this is also called the modulus of rigidity. Okay, so take note of this. So this is another material property. Okay, so its value represents the slope of the line, no, the G, no, the G here. So that is a tau over gamma, right? Okay, so that represents the slope. So that is rise. The rise here will be tau, no, the value of tau, and the run here will be the value um of the gamma, no. So that is the slope, and here, no, that slope, no, it can be computed as let's say the stress and strain in the proportional limit can be found, no. So that will be stress or tau sub PL over gamma PL, no. So that's how we compute G, or the modulus of elasticity. So we can we can use any point as long as it is within this line up to the proportional limit. Okay. Now for the unit, no, of the G, no, or the shear modulus of elasticity, no, that will be the same as the unit of tau, no, since gamma here, no, so this is expressed in radian, right? So radian is actually a dimensionless quantity. So the unit for G will be the same for as the unit, no, as the unit of tau. Okay, so in short, the unit for G, it's just Pascal or PSI, KSI, megapascal, no? So it depends, no? So that's the unit, okay, for G, or shear modulus of elasticity or modulus of rigidity. Okay, now we have here this table. So this is a table for average mechanical properties of typical engineering materials. So the materials here are listed, no? So this is these are some of the typical materials, no, that we are using in engineering. Okay, so as you can see here, no, we have here steel here, no. So let's say for steel of structural 836, no. Okay, so here, the specific weight is here. The modulus of elasticity is also indicated here. So this is 29 times 10 raised to 3 KSI, no, for its modulus of rigidity G, no. So this is also indicated here, no. So that is 11 times 10 raised to 3 KSI. Its yield strength also is given here, no. So for its yield strength in tension, compression, so this is these are given here. So this is 36 No, they are in KSI also for ultimate strength. Okay, in KSI for Poisson's ratio also, no, it is given here. Okay, so the value for the Poisson's ratio of a structural 836 steel, that is 0.32, ha. Okay, so just be familiar, no, with this table because we are going to use this, no, in our sample problems. Okay. The three material constants that we discussed, no, so that is the modulus of elasticity E, Poisson's ratio V, and modulus of rigidity G, no, they are actually related, no, with one another, no, by this equation. Okay, so this is the equation of the relationship of E, V or nu, and G. Okay, so this is G is equal to E over 2 times 1 plus V. So provided that E and G are known, the value of V or nu, no, it can be determined from this equation rather than through experimental measurement. Okay, so from the table actually, no, for 836 steel, the modulus of elasticity is 29 times 10 raised to 3 KSI, and its modulus of rigidity is 11 times 10 raised to 3 KSI. So if you are going to solve for the Poisson's ratio using the formula, so we are just going to substitute these values, no, this E and this G, no, and we can solve for small letter v or nu. Okay, so substituting the value of G, that is 11,000 KSI, and for the modulus of elasticity, that is 29,000 KSI, over 2 times 1 plus V. So solving for V here, no, so this is actually 0.32. So this is the Poisson's ratio for an 836 steel. And this is actually the value, no, that you will also see, no, in the table. Okay. Okay, so we are going to talk about now the generalized Hooke's law. So we are going to use the concept of Hooke's law, no, in solving for strains of materials that are actually loaded. Okay, so in this topic, no, we are going to talk about two loadings here, no, two axial loadings here. So that will be the uniaxial loading, and the other one is the multi-axial loading. So for uniaxial loading, no, we are going to directly use the concept of Poisson's ratio. So uniaxial, meaning to say, the material is only loaded in one axis. No, so in this case, no, this material, no, this is loaded, no, actually loaded in the x-axis, right? So this is uniaxially loaded, no. So to solve for the strain, no, in this uniaxially loaded material, no, we can use Poisson's ratio. So for uniaxial loading in the x direction, okay, so Poisson's ratio is V is equal to negative strain in the lateral direction over the strain in the longitudinal direction. So in this case, no, the longitudinal direction here, no, will be the strain in the x-axis. Okay, so the x-axis is the longitudinal direction here. And the lateral directions here will be two directions, no, that will be the y-axis and the z-axis. Okay, so again, the longitudinal direction here, since the load here is applied in the x-axis, so the longitudinal direction here will be the x-axis. The lateral directions here will be the y and z-axis. Okay, or direction, no? Okay, so from here, no, from this illustration, no, we can say that the Poisson's ratio is equal to negative strain in the z direction or strain in the y direction over strain in the x direction. Okay, so these are the formulas that we can use, no, to compute for the Poisson's ratio. So it can be negative strain in the z direction over the strain in the x direction, or we can also use negative strain in the y direction over the strain in the x direction. Okay, so here we can incorporate Hooke's law. So if you're going to compute, no, the shear stress, no, shear stress of this this material, no, we can use Hooke's law. So that is just equal to E times epsilon x, wherein epsilon x here, this is the strain, the normal strain, no? And the sigma x here, this is the normal strain, no? So we can say that epsilon x, or the strain in the x direction, that is equal to um, sigma sub x over E. Okay, so take note of this formulas. Okay, so from here, now we can use this and we can substitute this E sub x, no, or epsilon rather, epsilon sub x, no, in this formula. We can substitute it, no. So substituting that here, no, we can solve for epsilon y and epsilon z, no. So they will just be equal lang, no. So substituting epsilon x, no, so that will be sigma. Okay, so from here epsilon z, that will just be equal to epsilon y. So we will just cross multiply the denominators to the Poisson ratio v, no. So that will just be negative v times epsilon x, wherein the value of epsilon x from Hooke's law, that is sigma x over E. So take note, clause, of these formulas. We are going to use this. Okay. So we will now proceed to multi-axial loading, no, by using generalized Hooke's law. So for multi-axial loading, this is divided into biaxial loading and triaxial loading. Okay, so we will discuss first the biaxial loading. So Poisson's ratio permits us to extend Hooke's law for uniaxial loading to biaxial and triaxial loading. So for biaxial loadings, that means that the loadings here, no, are directed along two axes. Okay, so in this case, this is our reference axis, no? The x-axis is directed this way, the y-axis is directed this way, and the z-axis is directed this way. So let's say we have here this block. Okay, so this is an element, no, from a material. Okay, so let's say that in the x direction, okay, this is subjected to this normal. So since it is subjected to a loading, no, axial loading, no, that means that there will be a normal stress also here, no. So this will be the normal stress in the x direction. And then for the y direction, okay, so this is also subjected, no, to an axial loading. Therefore, there will be an axial for stress here, no. So here, meaning to say, no, we have here two, or this material, no, this material or this element, this is subjected, okay, to two loadings, no, loadings in the x-axis and loadings in the y-axis. Okay, so again, we are going to consider this element, no, and it is subjected simultaneously to normal stresses in the x and y directions. Okay, as shown in this figure. Okay, so this is the three-dimensional view, no, of the element, and these are the two. This is the two-dimensional view. Okay. So now, the strains, no, caused by the, let's say for ano muna ha, so we will first consider the sigma x, no, or the normal stress at the x direction. Okay, so this stress, okay, it will cause, no, this element, no, to be strained. No, so there will be strain in the first in the x direction, so there will be a strain in the x direction, so that will be epsilon sub x, no, and we know that epsilon sub x, we can compute it, no, incorporating the normal stress, that will be sigma x over E, no. So also the y direction or the lateral directions here will be the y direction and the z direction. Okay, so they will also experience strain due to the normal stress in the x direction. Okay, so the normal strain in y direction and z direction will just be the same. No, so that will be equal to negative v sigma x over e. So this is the formula that we derived, no, in uniaxial loading. No, so we can also apply this that here. Okay, so also, no, this element, this is also subjected, no, to this normal strain in the y direction. Okay, so due to this stress in the y direction, okay, this element will also experience strain in the y direction. And the strain in the y direction will be equal to sigma y over e. Okay, so this is the strain in the y direction due to the normal stress, okay, in the y direction. Okay, and also, no, due to this normal stress, no, in y direction, no, this element will also be subjected to strains, no, in other directions. Okay, it will experience strain in the x direction, okay, and in the z direction. Okay, so the stress or the strain, no, that will be experienced, no, by this element due to the normal stress in the y direction, so that will be epsilon x and epsilon z, and they will just be equal, and this will be equal to negative v. So this is sigma y, since the stress that caused this strain is the sigma y, no, so that will be sigma y here over e. Okay, so using superposition, no, we can combine these two effects, no, of the normal stresses, no, so we can um, combine them, no, and that's the concept for superposition, no. So this is a principle that states that the effect of a given combined loading on a structure can be obtained by determining the effects of the various loads separately and combining the results. So we will just combine the effect of the two normal stresses here. Okay, so we can write that the strain in the x direction. Okay, so the total strain here will be the strain caused by so this is the strain caused directly, no, by the sigma x. Okay, so this will be sigma x over e. So this is actually sigma x over e. And then we are going to combine also this sigma x, or epsilon rather, this epsilon x, no, due to the normal stress in the y direction. So there's also an effect. So we will combine this. So the formula for this is negative v sigma y over e. So we will just combine that here. So this is v sigma y over e. No? So we just factored out e here. No? So this will now be the total strain in the x direction. Okay, for this biaxially loaded element. Okay, now for sigma y, no, for sigma y, we will also combine the effects, no, of the two normal stresses. So for the normal stress in the y direction, its effect in strain, so this will be sigma y over e. Okay, so this is sigma y over e, and then we are going to combine, no, the strain in the y direction due to the sigma x. No, so the value for that is negative v sigma x over e. So we just substituted that here, or we sum that up that here, no. So since this is negative, or that is negative, so that will be negative here, v sigma x over e. So we just factored out 1 over e here, ha. Also for epsilon z, actually for epsilon z, no, even though there is no a normal stress in the z direction, but because of the stresses, no, because of the stresses in the x and y direction, there will be an effect also in the z direction. So there will also be strain in the z-axis. So we will just combine the strain in the z-axis due to the sigma y and the strain in the z direction due to sigma x. Okay, so that will be negative v sigma x over e, and then we factor out v over e here, ha. Okay, and then we have here negative v sigma y over e, so we just combine them. So this will be negative v over e sigma x plus sigma y. So this will now be the formulas, ha, in solving for strains, no, in in a biaxially loaded element. Okay. So this is which is Hooke's law for biaxial loading in the xy plane. So the normal stress in the z direction here is 0. Okay. Okay, so the first two equations, no, that is the epsilon x and epsilon y, or the strain in x direction and strain in y direction, they can be inverted to express the stresses in terms of the strains. Okay, so this will be the formula if what we want to solve is the sigma x, no, or the stress in the x direction, no, in terms of the if the given here are the strains in x and y direction. Okay, so these two formulas, these are just derived, no, from those formulas, no, for sigma x and sigma y. Okay, so take note, class, ha, that for biaxial loading, no, sigma z, or epsilon z rather, so the epsilon z, or the strain in the z direction, this is not 0. Okay, although the normal stress in the z direction is 0, no, still there will be a strain in the z-axis due to the stresses in the x and y direction. Okay, so we have formula for sigma epsilon for epsilon z. Okay, so that is the strain is triaxial rather than biaxial. Okay. Okay, now let's proceed to another multi-axial loading, no? So this is for triaxial loading, meaning to say all the directions here, no, all the three principal directions here, which are the x, y, and z direction, they are all loaded. No, they are all actually loaded. Okay, so there, meaning to say there will be a normal strain in the x direction, in the y direction, and in the z direction. So this is triaxially loaded. Okay, so Hooke's law for the triaxial loading in this figure. No, so this is obtained by adding the contribution of the sigma z, no, wherein the strain due to the sigma z, that is strain or epsilon, no, epsilon z is equal to sigma z over e, and also the x and y direction, they will also be affected, no, because of the stress in the z axis, no, so its effect in the x and y direction will be epsilon x and epsilon y, so they will just be equal. So this will be equal to negative v, no, so v here is the Poisson's ratio, ha, so v or nu, no, and then times sigma z over e. Okay, so we are just going to add this, no, to the strains in biaxial loadings that we already derived, no, in our discussion for biaxial loading. So we will just add this sigma z and this sigma epsilon, no, we will just add this epsilon z, okay, and then yung epsilon x and epsilon y. Okay, so let's say for epsilon x, no, from the biaxial loading, so the original formula there is 1 over e sigma x minus v times sigma y, no. So here we are going to add this effect, no. So this is due to the z, sigma z, or the stress in the z direction. So this will be v sigma z over e. So that will just be negative. This is negative here, ha. So this will be just added here, negative v sigma z over e. Okay, so that will just be added here, ha. Okay, also for epsilon y, so that is equal to this is the formula from biaxial loading, 1 over e sigma y minus v times sigma x. So we are just going to add this effect, no, due to the sigma z. So this will be sigma z v over e. Okay. Also for epsilon z, now we are just going to add this effect. Yeah, this effect. So in the in the in biaxial loading, our formula there is 1 over EV times sigma x plus sigma y, right? So here we will just add this effect. Okay, so this is sigma z over E. Okay, so this will now be the formulas for strain, no, in all directions, in the x, y, and z directions for triaxially loaded element. Okay. So take note that for all the equations here, no, they are valid for both tensile and compressive effects. It is only necessary to assign positive signs to elongations and tensile stresses, and conversely, negative signs to contractions and compressive stresses. So let's say here, for sigma x, sigma y, sigma z, no, if this stress, no, if the stresses here are in tension, so the sign convention for that will be positive. So if we substitute that value here, no, that will be positive if it's in tension. No, if that's stress. But if the stress is in compression, okay, so we have to include the negative sign. No, if we are going to substitute the value of that stress, no, in these formulas, ha. So again, for tensile stresses, it will be positive. For compressive stresses, no, that will be negative, ha. So take note of that clause. Okay, so in this case, class, all these stresses are all tensile, no? So they are all positive. Okay. Okay. Okay, so we are going to discuss another material property here called dilatation and bulk modulus. Okay, so when an elastic material is subjected to normal stress, its volume will change. No? So, for example, consider a volume element which is subjected to the principal stresses, sigma x, sigma x, sigma y, and sigma z. So this volume element, this is subjected to these stresses, no, in all the principal directions, no, there's a normal stress in the x direction, that is sigma x, in the y direction also, and in the z direction. So let's say that this volume element, its original, let's say this length, no, or the side of this element, let's say this is 1. Okay, and let's also say that its width, no, the length, or the value, no, this distance, no, of its width, let's say that this is also 1, and also this, no, this height, let's say that originally, no, this is 1. Okay, so class, upon application of normal stresses in all the three directions, no, in the xyz directions, no, so this element, no, it will be subjected to strains. No, so there will be a change, no, in the dimension in all the principal direction. So there will be a change in the x direction, z direction, and y direction. So there will be a strain in each direction. So for this side, no, so this is in the x direction, no, this side is in the x direction. So this will be deformed, no, because of the applied normal forces, no. So what will happen, so the original length, which is 1, no, there will be a strain, no, that will be added, no, to that original length, no. So this will become 1 plus epsilon x. Okay, same with this side, no. So this is originally 1. Okay, but because of the stress, there will be a strain, no. So this will become 1 plus epsilon y. Okay, same with this side. So this will become 1 plus epsilon z. And if we are going to compute, no, the volume, okay, the volume of this element, so that will just be the length times width times height, no, of this element, no. So we can solve for that. That is just the product of 1 plus epsilon x times 1 plus epsilon y times 1 plus epsilon z. But realize here, class, that all these strains, no, in x, y, and z direction, they are very, very small compared to um, 1, no. So we are going to neglect this product, no, since the strains are very small. So we have here 1 plus epsilon x plus epsilon y plus epsilon z. So you can actually try that, no, to you can try computing that, no. So you can try that in your calculator. You assume value for epsilon x, epsilon y, and epsilon z, and you will find out that that is just almost equivalent to 1 plus epsilon x plus epsilon y plus epsilon z. Okay, so you may try that, no. So you will just assume a very small value of
strains, no, in x, y, and z directions. And you will see that this is the result. This will just be approximately equal, no, to this result, or the result will just be approximately equal to this. No, so here, the change in volume per unit volume is called the volumetric strain or the dilatation. Okay, so this is the definition of dilatation, ha? So that is the change in volume per unit volume. Okay, so this dilatation, this is denoted as small letter e, and it can be written as, so here, this V, no, this is capital letter V. So this is the volume, okay, of the deformed element. Okay, so minus the original volume. So the original volume here is 1 times 1 times 1. Since those are the original length, width, and height of this element, right? So that will just be 1 cube. So V minus 1 cube, no? So if we are going to substitute the V from here, so this is 1 plus epsilon x plus epsilon y plus epsilon z minus this 1 cube is just equal to 1 then, no? So this will be minus 1. So this one, positive 1 and negative 1 will just be cancelled. Therefore, the formula for dilatation will just be equal to epsilon x plus epsilon y plus epsilon z. So that's how we solve dilatation. You just add, no, all the strains, okay, in the experience, no, by the element upon application of the stresses. Okay, so here you are also going to consider if it's a strain, no, or tawag dito, if it's elongation, no, so the strain is positive. If it's compression, the strain here is negative. Okay. So also, from the definition of dilatation, we can also write or rewrite the formula, no, for dilatation, no, based on its definition. This is change in volume. So this is change in volume over the original volume. Okay, so this is change in volume per unit volume. Okay. So these are the formulas for dilatation. Okay, also, if we use Hooke's law for triaxial loading, we can write the dilatation in terms of the applied stress. So from that, no, we have this formula. Okay, so in dilatation, no, our formula is actually E is equal to epsilon x plus epsilon y plus epsilon z, right? So the values for each epsilon, no, if we are going to substitute the value or the formula for epsilon x, y, and z, no, from the triaxial loading, no, of Hooke's law. Okay, so the resulting formula will be this. Okay, so this dilatation, no, so this is in terms of sigma x, sigma y, and sigma z. So instead of epsilon x, epsilon y, epsilon z, no, so there's also a formula like this. So again, this is from the Hooke's law for triaxial loading, how we just substituted the formula for epsilon x, epsilon y, and epsilon z, no, in the original formula for dilatation. Okay, so take note of these formulas, class, and familiarize yourselves, no, with the formulas, okay, that we are discussing here, because we are going to use all this, no, in solving sample problems. So when a volume element of material is subjected to the uniform pressure P of a liquid, the pressure on the body is the same in all directions and is always normal to any surface on which it acts. So this is one of the examples, no, of a material or an element, no, of a material that is subjected to normal stresses, no, in all directions, no, of the element in z, x, and y direction, no. So when you submerge a material, no, on a liquid, no, so what will happen is that or the elements in that material, no, it will be subjected to uniform normal stresses, no, in all directions, okay, in x, Y, and Z direction. So, shear stresses are not present since the shear resistance of a liquid is zero. So, this state of hydrostatic loading requires the normal stresses to be equal in any and all directions, and therefore an element of the body is subjected to principal stresses. So the principal stresses, let's say sigma x, sigma y, and sigma z, no, so they will all be they are all compressive stresses. Okay, so they will all be compressive stresses. Okay, so here, no, we will say that the stress here, no, that will be uniform pressure P, no. So let's say that all the normal stresses in all directions, no, they are all equal to P, no, as mentioned here, no, in the concept here that as mentioned here, no, the normal stresses are equal in any and all directions, no. So they are all P, no, they are all pressure P. Okay, so since they are all compressive, no, they are all compressive stresses, no. So our sign convention for that, for compressive stresses, that will be negative. So these are all negative P, no, sigma x, sigma y, and sigma z. Okay, so from here, no, from the formula of dilatation, no, in terms of sigma or normal stresses, no, so that is actually 1 minus 2v over e times sigma x plus sigma y plus sigma z, right? So substituting the values of sigma x, sigma y, and sigma z, which are all equal to negative p, so that will just become negative p plus negative p plus negative p, so that will just be negative 3p. Okay, so from here, no, we can generate this formula. Okay, so this is P over E. Okay, so we just cross multiply this, no? So this will become P over E, no? And then this 1 minus 2V, this will become the numerator in the terms, no, here at the left. So that will become including this negative 3, no? So that will become 3. Okay, this negative sign, so this negative sign, we just factor this out here, no? So this will be negative here, and then 3 times 1 minus 2v, and then this will become the numerator here, no? Okay, so this formula, P over E is equal to negative E over 3 times 1 minus 2v, we can actually introduce, no, another material constant here, and that constant is K. No, so this is called the modulus or volume modulus of elasticity, or the bulk modulus. Okay, again, K here is the bulk modulus. So we can get that K, constant K, no, from here. So this is E over 3 times 1 minus 2V. So this is the formula for volume modulus of elasticity, or bulk modulus. Again, this is K is equal to E over 3 times 1 minus 2. We were in E here. Okay, this is the modulus of elasticity. And then V here, this is the Poisson's ratio, right? Okay, and therefore, no, if this term is K, meaning to say, if you are going to solve for dilatation given this P, so this is the uniform pressure P of a liquid, no, over K given the bulk modulus, no, so we can also use this formula. Okay, let's solve sample problem number 1. A bar made of 836 steel has the dimensions shown in the figure. So this is the figure. So this is an A36 steel. So some of the material properties for A36 steel, no, that is found in the table that we talked about. So if an axial force P, which is equal to 80 kilonewton, so this is the axial force P. Okay, so this is applied to the bar. No? So determine the change in its length and the change in the dimensions of its cross-section after applying the load. The material behaves elastically. So here, this bar, no, this 836 steel bar, so this is subjected to a actually uniaxially load P, no? Okay, so we can apply uniaxial loading here, no? From generalized Hooke's law. So let's start solving this problem. Okay, so for this problem, we are going to solve the change in length. So the change in length will be the deformation, no, along the direction of the applied load P, no. So the change in length here will be elongation. Okay, it will elongate. And since it will elongate, no, in the direction of the applied load, no, so there will also be a change, no, in the lateral direction, no, of this bar, no. So its cross section, no, there will be a change, no. This 100 millimeter, this side, no, it will change, no, since it will elongate. So this 100 millimeter, no, definitely it will contract, no. And same with this 50 millimeter, this side, no, this is 50 millimeter, so this will also contract, no, since the longitudinal direction of the bar, okay, it will elongate. Okay, so we are going to solve that. So in short, for the length, no, that will be the elongation or deformation in the longitudinal direction, and the change in dimensions of the cross section, that will be the deformation, okay, in this in the cross section, okay, in this 50 millimeter side and in this 100 millimeter side. Okay, so we are going to solve them using the formulas, no, and the concepts that we talked about in our discussion. So for the first one that we are going to solve, we are going to solve the deformation, no, or the change in length. Okay, so to solve for the change in length, no, we can solve that using Hooke's law. Okay, so that is sigma is equal to E times epsilon. So in the epsilon there, no, we can solve, no, from the epsilon, which is the strain, no. Remember the formula for epsilon, that is actually, or strain, no, that is actually deformation over L, or the total, or the original length, right? So we can solve first for the epsilon, or the strain. But in order for us to solve for the strain, we have to solve first for the stress. Okay, so the normal stress here, okay, so this will be P. Okay, so P here, actually, this is ano ha, this is the internal normal force. Okay, so if we cut a section, no, in any part, okay, of this steel bar, no, the internal normal force P will just be equal to P as well. No, so that will just be 80 kilonewton. And here, class, no, so the normal stress that we are going to solve here, since the applied load P here is in the Z direction. Okay, so the normal stress here is sigma Z. Okay, so that is ano ha, our longitudinal direction here. Okay, and again, the value for P here will be 80 kilonewton, and that is actually equal to 80,000 newton. No? So we need to be consistent ha with our units here. Okay, so if you are getting confused, no, about the units, no, it's better for you to write, no, the units here beside the magnitude of the ano, no, or the value of the quantity. So for force P, that is 80,000 newton over the area. So the cross-sectional area here, wherein the normal force is perpendicular. Okay, so this is that area, no? That is the cross-sectional area. So that is 100 millimeter times 50 millimeter. Since this is a rectangular cross-section, no? So that is just base times height. That is just 100 millimeter times 50 millimeter. So in this case, this is Newton over millimeter squared. So the answer for this will be megapascal. So solving that in your calculator, 80,000 over 100 times 50, that is 16 megapascal. Okay, now we already solved for the sigma z, or the normal stress, no, along the z direction. Okay, so from here, no, we can solve for the strain, no, and from the strain we can solve for the deformation. Okay, so in the problem, no, it is stated that the steel is an 836 steel. no? So from the table, no, there's actually a derived modulus of elasticity already for A36 steel, and that is 200 gigapascal. Okay, so from here, no, we can apply Hooke's law. Again, Hooke's law is sigma is equal to E times epsilon. Okay, so we can solve for the epsilon z, which is the strain, no, in the z direction. So that is just equal to the normal stress at the z direction over E of the steel, or the modulus of elasticity of the 836 steel. So substituting the values here for sigma z, that is 16 megapascal, and for E or modulus of elasticity of the steel, that is 200,000 megapascal. So take note that strain, this is a dimensionless quantity, so megapascal will just be cancelled here, right? So here, this will be 0.00008 millimeter per millimeter, since the unit that we use here are megapascal, no? So in megapascal, that is Newton per millimeter squared. So the unit that we're going to use here is millimeter per millimeter, though it's just actually cancelled, right? But we are just going to indicate here, no, this unit, millimeter per millimeter. Now, after we solve for the strain, no, in the z direction, no, wherein the elongation will happen, no, again, the elongation, it will occur, no, in the direction of the applied load. So okay, so we are going to solve here the elongation. So for the formula of elongation, no, from the formula of strain. Okay, so the formula for strain, that is deformation over the original length. Okay, so we have here the original length. The original length of this steel bar is 1.5 meter, right? So we are going to use that, and then we are also going to use the value of epsilon z that we computed. So substituting the values here, no, 0.00008, that will be the epsilon z, is equal to the delta z, so this is the deformation that we are solving, times 1,500 millimeter. So we just converted 1.5 meter into millimeter. So solving for delta z, so that will be 0.12 millimeter. So this is now the deformation, no, or the change in length, okay, that we are solving for this item. Now for the second one, no, so this is the change in the dimensions of the cross section. Again, no, if this bar will elongate, the cross-sectional area, it will decrease. Okay, so we are going to solve for the decrease, no, in the length 100 millimeter and this 50 millimeter. No, we are going to solve that, no. So in the table, no, as we know, uh, it's already derived, no, the Poisson's ratio for an A36 steel, no, so that is 0.32 from the table. Okay, so from here, no, we can use this solution, or this data, no, this Poisson's ratio, in solving for the strains, no, in the lateral direction, no, of this bar. So the lateral directions here, let's say our reference axis here, y-axis for this, x-axis, and then z-axis, no. So the lateral directions here are x-axis and y-axis. So for the x-axis, no, so this is the x-axis. So this 100 millimeter, no, so there will be a strain here, no, that is epsilon x, and then also for this is in y, y direction. So this 50 millimeter, there will also be a strain there. No, so that strain is epsilon y. Okay, so here, no, this epsilon x and epsilon y, they are the strains in the lateral directions. Okay, so from the formula, no, in our discussion, no, for Poisson's ratio, that is actually the strain in the lateral direction over the strain in the longitudinal direction. So the longitudinal direction here is the z direction, right? So the lateral directions are epsilon x and epsilon y, okay, or the strain in x direction and strain in y direction. So these are negative, as we have talked about already, no, in our discussion. Okay, so from here we can solve the strain in the x direction and the strain in the y direction. So if after we solve the epsilon x and epsilon y, we can actually solve already for the deformation, right? By using this same formula. Now, epsilon is equal to delta, or the deformation, over the original length. Okay, so from here, substituting the value of the Poisson's ratio, which is 0.32, and we already solved for the epsilon z. So the epsilon z is this. Now, so from here, we can solve for the strain in x direction and strain in y direction. So this will just be negative 0.32 times 0.00008. So the value for this is negative 0.0000256 millimeter per millimeter. So this negative sign, it indicates that epsilon x, or the strain in x and y direction, they are both contraction. Okay, so from here, no, from the computed epsilon x and epsilon y, okay, we can compute for the deformation, okay, or the delta, let's say for the x direction. So the x direction here, the length in the x direction is 100 millimeter. Okay, so this is the original length, no, of this side, no, of this 100 millimeter. So from here, no, we already manipulated this, no, so this is delta in the x direction, no, or the deformation in the x direction is equal to epsilon x. This is the value of epsilon x, and our Lx here is the length in the x direction, which is 100 millimeter. So substituting these values for delta x, so that will just be negative 0.0000256 times 100 millimeter. So this will now be the deformation, no, of the, or the, of this side, no, of this 100 millimeter side, no, in this, in the cross section, okay, of this bar. So this will now be the answer for that direction. Now for the y direction, no, this 50 millimeter, no, there will also be a strain here. Okay, so that's the strain here will be epsilon y. So to solve for the deformation, that will be strain times L. No, so our Ly here will be 50 millimeter. Okay, so substituting the values here, so this will just be negative 0.0000256 times 50 millimeter. And this will be now the deformation in the y direction. So this will now be the answers, no? So this is the change in length, and this is the change in dimensions of the cross section. So this will now be the answers for this problem. For sample problem number 2, the copper bar in the figure is subjected to a uniform loading along its edges as shown. If it has a length A is equal to 300 millimeter, so this is the A, no? Okay, and then width B is equal to 50 millimeter, so this is the B. And then the thickness T, so that is 20 millimeter. Okay, so before the load is applied, determine its new length, width, and thickness after application of the load. So we are going to take the modulus of elasticity, no, for copper, that is equal to 100 gigapascal, and for the Poisson's ratio of a copper, so this is equal to 0.34. Okay, so let's solve this problem. Okay, so for this problem, we are going to solve the new length. Okay, so the length here is A, and then the new width, so the width here is this B. Okay, and the thickness, the thickness here is this, no, thickness T. So, uh, upon application, or after application, okay, of these loadings, as you can see, no, in this illustration, this copper bar, no, this will deform. No, this will deform. So here, as you can see here, no, this copper bar, this is loaded in two directions. In this direction, no, this is the loading for this direction. Okay, and for this direction, this is the loading. Okay, so here, since there is no given reference axis here, no? So let's say that this direction, no, let's say that this is x direction or x-axis. Okay, so this is the x direction, and let's say that this is the y direction. Okay, and let's say that this, no, this is the z direction. Okay, so this direction, no, along this length A, again, this is the x direction or the x-axis. And then this direction, no, along the width B, this is the y direction. And this axis, no, along the, or the direction along the direction of the thickness, no, so this will be the z direction. Okay, so as you can see here in the x direction, no, this is the ano no, loading. Okay, so this is actually in tension, right? So this loading in the x direction, this is tension, right? And here in the y direction, okay, the loading here is in compression. No, in the z direction, there is no ano ha, there is no loading applied. No, so we can say that this copper bar, no, so this is biaxially loaded. Okay, this is loaded in two directions, in the x direction and in the y direction. So the question here, class, is the new length. Okay, so to solve for the new length, the new width, and the new thickness, no, we have to determine the deformation. Okay, so after we determine the deformation, since the question here is new length, so we have to sum up, no, the that computed deformation, okay, to the original length, original width, and original thickness to solve for the new length, new width, and new thickness. Okay, but before we can solve the delta or the deformation, no, we have to solve first for the epsilon. Okay, because that is our formula for that, right? Epsilon is equal to delta or the deformation over the original length. Okay, so we have to solve first for the strain. So as we can see here, no, there will be strain, no, in all directions since this is by actually loaded, no, loaded element or copper bar. Okay, so there will be strain in x direction, strain in y direction, and there will also be a strain in the z direction. Although there is no stress in the z direction, but there will still be strain in the z direction, ha? So we already talked about that in our discussion about biaxial loading, ha, using generalized Hooke's law. Okay, so but before we can solve for those strains, no, for those epsilons, no, we have to we need to have sigma or the normal stresses. But here, no, by inspection in the given figure, now we can say that the normal stresses here, no, for the x direction, this is 800 megapascal. Okay, so this is in tension class. Okay, so that will be positive. And then for the y direction, okay, the normal stress here is actually 500. Now, so this is given here. And this is in compression, right? So this will be negative. And for the z direction, the normal stress is 0. There is no applied ano ha, normal stress or loading, no, in the z direction. So since we already have this sigmas, no, or normal stresses, we can now solve for the strains, no, using the formulas that we derived in our discussion in the axial loading using generalized Hooke's law. So we will start with the strain in the x direction. Okay, so this is already our formula for this, ha. So the strain in the x direction, this is the combined strain, no, due to the normal stress in the x direction, of course, and the applied stress or loading in the y direction. So this will be the ano, stress in the y direction, ha. So this is already combined. So this is already the formula for the total strain in the x direction. So here, the modulus of elasticity for copper bar, this is given in the problem. Okay, and sigma x, no, we already have the value for sigma x. For V, or the Poisson's ratio, this is also given in the problem, no, and then sigma y, this is already the value for sigma y. So substituting the values here for the formula, no, or in the formula, this is 1 over 120,000 megapascal times 800 megapascal for sigma x minus V. Our V here is 0.34, no? That is given in the problem. And our sigma y here is negative. So you have to indicate here, ha, the negative sign. Okay, so don't forget that class, ha. Okay, so in solving for epsilon x, or the strain in the x direction, this is equal to 0.00808. Okay, now for the strain in the y direction, okay, so this is the formula for the strain in the y direction. So this is already the, the combined strains, no, caused by the stress in the y direction and the stress in the x direction, ha. So we will just substitute the values here. So this will become 1 over 120,000 megapascal times negative 500. So that is our sigma y, that is negative 500, minus our Poisson ratio is 0.34, and our sigma x is 800. Okay, so solving this clause, so the value for this, if you input this in your calculator, this will be negative 0.00643. Okay, so the negative sign here, class, indicates that the strain in the y direction is compression, ha. Okay, now for the strain in the z direction, again, class, we already talked about that in our discussion for biaxial loading using generalized Hooke's law. Even though there is no stress in the z direction, there will still be, no, a strain in the z direction, ha. Okay, for biaxial loading. Okay, so this strain, no, in the z direction, this is caused by the stresses in the x and y direction. Okay, so substitute lang natin, class. Let's just substitute the values here. Okay, so this is negative V, Poisson's ratio, over E times sigma x plus sigma y, ha. So substituting the values here, this will be negative 0.34 over 120,000 megapascal times 800 minus 500. So this is minus, ha, since our sigma y, that is negative, ha. Okay, so solving this, okay, so this will be negative 0.00085 Okay, so this will now be the values of the strains in all direction, x direction, y direction, and z direction. So analyzing these values, no, so for the strain in the direction x, so meaning to say, no, this length, no, in the x direction, the strain here, since the strain here is positive, meaning to say it will elongate. Okay, so this length A, it will elongate, ha, since the strain here is positive. Now, for the y direction, okay, so the side, this side is the, no, this is the width B. Okay, so this width B, no, since the strain in this direction, no, this is y direction, since it is negative, meaning to say, this width B, this will contract, ha. This will contract, class, this will contract. Okay, now for the strain in the z direction, okay, so the value here is negative, ha, meaning to say this thickness, okay, this thickness will also be decreased. Okay, so it will contract. Okay, so from here, okay, since we already solved for the strains, we can now solve for the deformations. Okay, so after we solve for the deformation, class, how we have to add that or subtract that, no, in the original length, original width, and original thickness, ha. So the formula for the deformation, okay, so from this formula, epsilon is equal to delta over the original length. So we already have the values for all the epsilons. Okay, so we can now solve for the corresponding deltas or deformation, no? So to solve for the new length A, okay, so this will be denoted by A prime. So this will be the new length. So the new length will be the original length, which is 300 millimeter, plus since this is elongation, ha, so this will be plus the deformation or the delta. So the delta here will be epsilon times L. So the epsilon in the x direction is 0.00808, and the original length, no, this original length A, this is 300 millimeter, ha. Okay, so solving this, so the new length A will be 302.424 millimeter. Okay, so this will be the new length is. This will now be the answer for that, ha? Now, for the new width, okay, so the new width, so our width here is B. So the new width, let's say B prime, no? So the original width here, class, is 50 millimeter. And in this direction, the epsilon or the strain is negative. So this will be subtracted, no? The deformation will be subtracted. So it's negative here, ha? Okay, so the deformation again is epsilon in the y direction times the length, no, in that direction. So the original length in that direction is 50 millimeter. So solving for the new width, this is 49.6785 millimeter. So from 50 millimeter, it became 49.6785 because it contracted. Okay, it was shortened. Okay, or it decreased. Okay, so that will be the new width. Now, finally, for the new thickness. Okay, so for the new thickness, the original thickness is 20 millimeter. Okay, and the strain here is negative also. So this will be negative here. Okay, so the original thickness, again, 20 millimeter. Okay, so to solve for the new thickness, this is 19.983 millimeter. So this will now be the answers for this problem. Let's proceed now to sample problem number 3. The principal stresses at a point are shown in the figure. If the material is aluminum, for which the modulus of elasticity is 10 times 10 raised to 3 KSI, and the Poisson's ratio here is 0.33, determine the principal strains. Okay, so this is the given element of the material, ha? Okay, so the material is aluminum, ha? Okay, so let's solve this problem. Okay, so for this problem, no, we are going to solve the strains in the principal axis. So that will be the strains in the X, Y, and Z directions, no. So in this case, no, since there is no given reference X, Y, and Z axis here, no, so let's say that this direction, no, so this is the X direction, and then let's say that this is the Y direction, okay, and let's say that this is the Z direction. Okay, okay, so for this problem, no, from the given illustration, okay, so we can say that the stress, okay, in the X direction, that is 15 KSI, no. So as we can see here, this is in compression. Okay, so this is in compression, so this will be a negative, this will be negative here, no? Also, for the stress in the Y direction, okay, so as we can see, this is 26, and this is also compression. Okay, so this will be negative here. Now, for the stress in the Z direction, this is 10 KSI, and this is in tension. No, so this will be positive here. No, so since this is, there are three stresses here in all the directions X, Y, and Z, meaning to say, okay, this material or this element, no, this is triaxially loaded. Okay, so this is loaded in all direction, in X, Y, and Z direction. So we are going to use the formula for solving strain, no, in triaxial loading, no, using generalized Hooke's law. Okay, so the formula for the strain in the x-axis that we derived, no, in our discussion, okay, for triaxial loading. Okay, so this is already the total strain, no, in the x direction. Okay, so this is already the strain due to the stresses in the x, y, and z direction. Okay, so we are just going to substitute the values here. So the modulus of elasticity is given in the problem. So substituting these values, no, so this will become 1 over 10,000 KSI times sigma x is negative 15 KSI minus our given Poisson's ratio is 0.33, and the value of sigma y is negative 26, and then plus sigma 2, sigma z, that is 10 KSI, ha. Okay, so solving for the epsilon x, or the strain in the x direction, this is negative 0.00097. Okay, since the in the x direction, no, the stress here is compression, no. So meaning to say, the strain in the x direction, it will really be ano, contraction, no. It will be shortened, no. Okay. So also, we are going to, so this is already the answer for the strain, no, in the x direction. Now for the strain in the y direction, so this is the formula. So again, this is already the combined strain in the y direction due to the stresses in the y, x, and z direction. So we will just substitute the values here. So this will be 1 over 10,000 times negative 26 minus 0.33 times negative 15 plus 10. Okay, so solving this, this will be negative 0.002435. So in the y direction, the strain is negative, meaning to say it will contract, no, the that in that direction, no, this element, no, it will contract. Okay, so lastly, for the strain in the z direction, okay, so this is the formula. So this is already the combined strain in the z direction due to the stresses in the z, x, and y direction. So substituting the values here, this will be 1 over 10,000 times 10, okay, minus 0.33 times negative 15, okay, minus 26. So the value for strain here will be 0.002353. So this is positive because this side, no, this in this direction, the stress is tension. So it will really elongate. So this will now be the answers for this problem. For sample problem number 4, if the rectangular block shown in figure 1025, so this is the figure, this rectangular block, no, this is subjected to a uniform pressure of P is equal to 20 psi. So this uniform pressure, no, this will act, no, in all direction, in the x direction, y direction, and z direction, and they are all P, which is equal to 20 psi. So determine the dilatation and the change in length of each side. So take modulus of elasticity equal to 600 psi and the Poisson's ratio, this is 0.45. So let's solve this problem. Okay, so for this problem, we are going to solve the dilatation and the change in length of each side. Okay, so here, it is mentioned in the problem that this rectangular block, no, this is subjected to a uniform pressure P. Meaning to say, no, this rectangular block, no, this will be subjected to a compressive normal stress, no, in all direction, in X, Y, and Z direction. Okay, so here, since the given is the stress, no, or the pressure, no, so the formula that we are going to use here to solve for the dilatation, no, so that will be the formula, no, involving stresses. So the formula for that will be 1 minus 2v over e times sigma x plus sigma y plus sigma z. Now, since again this rectangular block is subjected to uniform pressure P, no, so that pressure P will be the stress, no, in all direction, no, in x, y, and z direction, and that is compressive, so that will be negative 20 psi, no. So substituting this value, okay, for sigma x, sigma y, and sigma z, so this will become, okay, 3 times negative 20 na lang, no? So, since they are all equal, no? They are all negative 20 psi, okay? Then, our Poisson's ratio here, this is given, 0.45, and our modulus of elasticity is also given, 600 psi. Okay, so from here, class, we can solve for the dilatation. So, the dilatation class here is negative 0.01. So the unit here is inches cube, okay, over inches cube. Okay, so this will now be, but actually class, this is ano, no, dimensionless. We can just cancel this out, but we will just write that here, no, as indication that the units, okay, of the lengths here are inches, ha? So this will be the unit, inches cube over inches cube. So this will now be the answer, no, for dilatation. Okay, now, let's proceed now to the second question, which is the change in length of each side. So if you're going to solve for the change in length, that will be the delta or the deformation, right? So we will use epsilon is equal to delta over L, no, for, to solve for that delta. So we have to solve first for the epsilon, okay, or the strains, no? So for the strains here, no, so this is triaxially loaded, right? This rectangular block, no, so this will be triaxially loaded. It will be loaded in the x, y, and z direction. But here, class, all the stresses, no, or the stresses in all directions, they are all equal. Okay, so the stress is 20 psi compression, right? So meaning to say, all the strains here, no, in all directions, they will also be equal. Okay, so the strain in the x direction will just be equal to the strain in the y direction and in the z direction. So meaning to say, no, for all the strains, no, in all direction, this will just be equal to 1 over E times sigma x minus V times sigma y plus sigma z. Okay, so this is for sigma x, no? So this will just be the same, no, for sigma or epsilon rather, for epsilon y, no? This will just be the same since all the sigma here, okay, they are all equal. Okay, so it will just be the same for all the strains in all directions. So the strain here, substituting the values, 1 over 600 psi times negative 20 psi minus 0.45 times negative 20 minus 20. So the answer for the epsilon or the strain is negative 0.00333 inches per inches. Okay, so this will now be the the strain in all directions. So this is negative because all the directions here, they are subjected to compressive stresses. So of course it will contract, no? Okay, all the sides will contract. Okay, so same here, class, in dilatation. So by definition, dilatation, class, is the change in volume over the original volume. So in this case, since the answer is negative, meaning to say the volume here, class, decreased. No, so the volume here, it decreased since it's negative. Okay, so for the deformation, for side A, side B, and side C, we will use this epsilon. Okay, so this will be the epsilon for all the computation of deformation. So for the deformation in this side A, okay, so this will be delta, so epsilon times L. So the epsilon is this, and then the original length is 4 inches. So the change in length of side A, so this will be negative 0.01332 inches. So this will now be the answer for this side. Now for the side B, okay, so this is the side B. Okay, so our epsilon is the same, and then the length of B is 2 inches. So the change in length of side B, this will be negative 0.00666 inches. Okay, lastly, for side C, so this will be the epsilon times the length, original length of side C, which is 3 inches. Okay, so this will be negative 0.00999 inches. Okay, so this will now be the answers for this problem. That concludes our discussion. I hope that you learn and attain the learning outcomes for this topic. See to it that you answer the corresponding course material assessment task for this topic. So that will be submitted, no, on our next meeting. Okay, so I will see you again, class, in our next meeting. Keep safe always. God bless. Bye-bye. Aral mabuti, class. Bye-bye.